Okay, thank you, sir. So, I am Anuradha. On behalf of the Science Club, I welcome you all in today's talk on Fundamentals and Finality, the life and work of Steven Weinberg by Professor Sunil Mukhi. Today's talk is about Steven Weinberg, who passed away 2 months ago. As you many of know, he had received a Nobel Prize in Physics for his work in unifying fundamental forces. Apart from his research, he was a great educator, a speaker, and had a wide range of interests. Professor Sunil Mukhi will be talking more about his work and life. Most of us don't need an introduction of Professor Sunil Mukhi, but nevertheless, he is a great theoretical physicist, and his research work on string theory, quantum field theory, and particle physics. He has made various important contributions in these fields. I request if you have any suggestions, comments, questions, please type them in the chat window. We will take them later. With these few words, I invite Professor Sunil Mukhi for this talk. We welcome you, sir.
Thank you so much. I'd like to thank the Science Club for this kind invitation to give this talk, and also all of you for sparing a Saturday afternoon when you could probably be doing other things to come and listen to it. I'll try to keep it quite non-technical, and I hope you'll find it interesting. So let's, oh, I'm getting a call, just checking in case I need to take this. Hello? Yes? Yeah. Okay, sorry about that. Good. Okay. So I'll be talking about Steven Weinberg, and before I get started on the actual talk, let me just mention that I'll be using images, videos, and quotes that may or may not be in the public domain, and I'm using them under fair use criteria. And yeah, let me start. So here is a very young Steven Weinberg. And let me start by giving you, of course, this is a picture of him standing in front of a blackboard diagram based on his very famous model called the Standard Model of Particle Physics. And here is a nice quote. He says, there are symmetry principles that dictate the very existence of all the known forces of nature. That's a very striking and strong statement. Weinberg was born in 1933. He wrote several papers in his lifetime. We'll come to that. And was a very acclaimed physicist. He won the Nobel Prize, other awards, and passed away, as the organizers just said, a couple of months ago. Okay, now before I speak about him, it's nice that you hear him in his own words. And so through this talk, you will find 3 or 4 video clips of Weinberg speaking, and I hope you can hear clearly. If not, you can tell me at the end. Each clip is only about 30 seconds or 45 seconds. So we'll start with this one from an interview he gave in 1990. The interviewer asks him what it is that he wants to know, and he gives his characteristic answer.
What is it you want to know about the universe?
I just want to know one thing, which is why things are the way they are. I think that we've come a long way. You know, if you ask any ordinary question about everyday things, why is the sky blue? Why is water wet? We actually know the answer. We meaning the whole body of physicists and chemists and biologists, we know the answer to these things. Then you ask, why are those things the way they are? And we've come a long way. We now have a picture that underlies atomic physics in terms of the properties of elementary particles. It's sometimes called the Standard Model, which is a way of saying we all believe it and use it without being absolutely sure of anything. And then you ask, why is that true? Well, that's what I want to do. I want to trace these chains of why down to their roots.
So I hope you could hear that clearly. Were you able to hear it?
Yes.
Okay, good. Okay, so as you see from that brief comment, by the way, these videos are available on YouTube and you can see the full versions. From that brief comment, you see that Weinberg was interested in the why questions. That was his thing. And let me trace his career and then start to tell you about those why questions. So Weinberg was born in New York City in 1933. And he studied at a very interesting place. He studied at the Bronx High School of Science, which besides himself has produced 6 physics Nobel laureates, so total 7, as well as a bunch of other famous scientists, as well as a Nobel laureate or 2 in other fields than physics. Let's see the physics Nobel laureates. There's Leon Cooper, who got the Nobel Prize for BCS theory of superconductivity. There's Sheldon Glashow, who will be mentioned again in this talk. He shared the Nobel Prize with Weinberg and also Salam. And in this case, actually, Glashow and Weinberg were classmates. So they were in the same batch in the same school. Roy Glauber, who got a Nobel Prize for optical coherence. Russell Hulse, who discovered the first binary pulsar along with Taylor. Hugh Politzer, who discovered a property of strong interactions called asymptotic freedom, and Melvin Schwartz, who discovered the muon neutrino. This is a bunch of Nobel laureates from that school. Other famous students from that school are Lenny Susskind, one of the inventors, if you like, of string theory and one of its most powerful proponents. He's at Stanford. And science popularizer Neil deGrasse Tyson also studied in the Bronx High School of Science. Okay, so of course, degrees, well, these are all prestigious universities. Weinberg went to Cornell, got his BSc there, went to Princeton and got a PhD in 1957 at the age of 24. And then he had postdoctoral fellowships at Columbia, and there, which is in New York City again, and then at the opposite end of the US on the West Coast in Berkeley. And after that, he got actually a faculty position in Berkeley in 1960, by which time he was 27 years old, quite young for a faculty position. And he stayed there for another 6 years until final. And during these 6 years, he made a very important visit to Imperial College London over the summer, which I'll tell you about, at the invitation of Abdus Salam. Thereafter, he moved back to the East Coast to Harvard and was there from 1966 to 82, first in a kind of temporary position and then in a kind of chair professor position. And in between these two positions, he took a year off and went to MIT. Now, MIT is in the same town as Harvard. This is the town of Cambridge, Massachusetts, and they are about half an hour walking distance apart. But they are quite different institutes. And for some reason, the year at MIT was very fruitful. And this paper that he wrote, which I'll talk about, which won him the Nobel Prize, was written in 1967 in that year in MIT, though he had been in Harvard previously and later. He was also in Harvard at the time he got the prize. Okay. Now in 1982, he moved to the University of Texas, Austin, and he stayed there till the end of his life, nearly 4 decades. And you can see from these pictures that Harvard is something, it represents somehow the old world, and Texas, the university is more modern. And we'll see later in this talk that the cultural difference between Harvard in a very liberal state of Massachusetts and Austin in a very conservative state of Texas, that difference had some interesting impact on Weinberg on the subject of guns. So we will talk about guns, but only at the very end of this talk. Okay. Weinberg wrote around 180 papers. That's a lot, but of course, there are many people who have many more than that. And essentially all his work is in theoretical high energy physics or cosmology. He's not one of those people who explored broad areas of physics, though he did talk about them, he studied them, he wrote about them, he knew a lot of physics beyond what he did, like any good physicist, but his research output was essentially all in this field. His first paper was written in 1956 at the age of 23. And in the next 6 years after that, he started to establish himself as a very solid and insightful researcher. The papers were not necessarily earth-shaking, but they were very good. They were very solid, and they were about contemporary issues that people were thinking about. Some of the papers were single author, some were collaborative. But after 62, started a series of events which led him to write the paper that would really make history. Now, one can discuss at least 8 or 9 major themes in Weinberg's research, all within this area of high energy physics and cosmology. But obviously, I can't do that in a 1-hour talk. So I selected 3 research topics to discuss. The first is the electroweak theory, which is the one that led to the Nobel Prize. The second is axions, and the third is the cosmological constant. Now, the first one I know well. Of course, I've read his paper on the electroweak theory and studied it many times. On axions and cosmological constant, I'm not that much of an expert, and I'll just tell you what I think I understood of the impact of those works. But after that, I'd like to spend quite a lot of this talk discussing his textbooks, his popular books and articles, and his public advocacy for certain causes that he believed in. So let's start. So I'll give you a little background about this electroweak theory. So the puzzle was, in the late 50s, people were asking, what is the theory underlying the weak nuclear interaction? This is the interaction responsible for radioactive decay. And it was known that it's an independent interaction from electromagnetism. It has nothing to do directly with electromagnetism nor with gravity. So it's a new type of interaction. And of course, there were many kinds of radioactive decay. And the one that weak interaction produces is beta decay. There's also alpha decay, and that one is associated to the strong interactions, which are the fourth kind of fundamental force. So people were also trying to look for a theory of that, but in particular, they wanted a theory of the weak interactions, which would allow us to do things like calculate the rate of nuclear beta decay from first principles, and also the decay rate of leptons, a certain class of particles, which includes muons that come to us in cosmic rays. Now, the electromagnetic interactions by this time were well understood thanks to quantum electrodynamics. This is the first relativistic quantum field theory, QFT for short, and it won the Nobel Prize in 1965 for Feynman, Schwinger, and Tomonaga. This is a whole other subject, obviously, and I won't go into any details here. But these interactions were well understood because of this QFT, which allowed us to calculate to phenomenal precision the probability of any electromagnetic process. Okay, and Weinberg's contribution basically allows us today to calculate with comparable precision the rate of weak interaction processes and to predict how they operate. Now, interactions like muon decay are not electromagnetic, and one particular feature of them, which is not shared by electromagnetism, is that these weak interactions violate parity. Parity is left-right symmetry or mirror inversion, and it's violated by the weak interactions only out of all the interactions in nature. So it's very special that way. And one characteristic feature of weak interactions is that often, not always, but often, a weak process gives rise to neutrinos. The other way you can be sure, namely, if you see neutrinos in a process, it's definitely a weak interaction process. But there are some weak interaction processes where you don't see neutrinos also. Okay, and neutrinos are very special particles. They're extremely light. They're extremely hard to detect, but they're there. They do exist. And the characteristic weak interaction process is what you see in this figure, that a muon just at rest, if you can isolate it and leave it at rest, will decay quite quickly actually into an electron and two types of neutrinos. So it's a 3-body decay. Now, Fermi had an idea already, I think, in the 30s of what the decay should look like. And he had a diagram, which I've represented here, where you see here time is sort of running from bottom to top. You see a muon coming in, and then you see 3 arrows going out. Actually, one of the arrows looks like it's coming in, namely this new bar, but actually it's an outgoing antiparticle. So this is the way physicists write their arrows. But basically in the upward direction, you see an electron, a muon neutrino, and a electron antineutrino, 3 particles coming out. Now, of course, this is the process, and Fermi gave a kind of equation which models this process and basically models it as a 1 goes to 3 process, namely 1 incoming, 3 outgoing. But there was a later proposal that after Fermi, that maybe that's not what the process really is. Maybe the process is that there's a new particle called the W for weak interactions, such that the muon gives off only a W and a neutrino, and then the W at some later time splits into an electron and an antineutrino. Okay, outgoing particles are the same in both, but the calculation is different. And at low energies, both these diagrams give similar probabilities, but they differ at high energies. And the reason, exactly because they differ at high energies, people were keen to fix that problem and to make sure that they had a theory which was valid at very high energies. That was always the goal. Okay, and this hypothetical W boson, W particle, is supposed to be a boson of spin 1. So it obeys Bose statistics, it communicates the weak force, and it's very analogous to the photon, which also has spin 1 in units of h bar and communicates the electromagnetic force. Okay, now the idea of proposing weak force carriers was not just to have an analogy with electrodynamics. It was realized quite soon that if such things don't exist, and if the correct diagram is Fermi's original diagram, then his theory must break down at high energies. Basically, you cannot have any process where a fermion splits into 3 fermions. Here it was a muon and then electron and two neutrinos, all are fermions. Such a process you cannot have without an intermediary, because if you do, then the corresponding equation has a dimensional issue which causes it to break down at sufficiently high energies. And by assuming the presence of an intermediate force carrier, you can solve this breakdown problem. Actually, this problem could also have been phrased in electromagnetism, and there you can clearly see that there's an approximation to electromagnetism which involves a 4 fermion interaction, but that is a good approximation only at low energy, and at high energy you have true electrodynamics. Similarly, people thought they would find the true theory of weak interactions in this way. And Schwinger observed that there's, of course, it was obvious to people, I think, even then, that because this is the weak force and not the electromagnetic force, the carrier, this W particle, must have a mass, because a massless particle mediates a long-range force. So, for example, the photon mediates the electromagnetic force, which is so long-range that we can see light from the sun and from stars and from other galaxies and so on. Okay, but the things that are given off in weak interactions don't manage to make it from even like a few inches away. So you really need to observe them very close. They have a very short range. Okay, and because of that, the weak force carrier must have a mass. Okay, so mass of a force carrier is always associated to short range nature of interactions. Now, what is the reason why the photon is exactly massless? It's not an approximate statement. We believe it's exact. This is due to a symmetry of Maxwell's equations called gauge invariance, which is needed for consistency of quantum electrodynamics. Without gauge invariance, the theory falls apart, or again becomes inconsistent at high energies. With gauge invariance, on the other hand, it's consistent, but the photon must be massless. Luckily, it is massless in real life, so everybody is happy. The problem, though, is that the weak force carriers need to have a mass. Therefore, it seems they should not have gauge symmetry, because gauge symmetry is present only on massless particles. But without gauge symmetry, consistency is lost, and the theory, even with this weak force carrier, will again break down at high energies. And here we are seeing a theme which is recurrent in the study of quantum field theory, which is that unless you're careful in making your theory and you follow principles, not just some practical ideas or writing some generic equations, unless you do that, your theory will break down at high energies. And therefore, there's a privileged class of theories, those which actually survive at high energies. They're called renormalizable theories. And so this is a kind of problem where people were stuck for many years. Without gauge symmetry, the theory breaks down. With gauge symmetry, it can't describe weak interactions. Okay, now enter Glashow. He actually was an early entrant into this subject in 1960 on a visit to Copenhagen from Harvard, where he was also based. he wrote a paper by himself proposing a quantum field theory of weak and electromagnetic interactions where there was such a W particle and there was an additional particle called the Z or the Z. In America, they say Z. Okay. And the interesting thing is that in his theory, these particles were related by a certain kind of gauge symmetry, which is called non-abelian. Non-abelian is based on some non-abelian algebra, and most of you have had a first-year course in math, so maybe you have heard about Lie algebras. Probably you haven't studied them. In this case, SU2 is a Lie algebra. It's similar to the rotation algebra, and it rotates these W and Z particles into each other in the theory. Now, Glashow's theory was very good, okay, but it couldn't be correct. It was very close to the correct theory, but the mass of the force carriers had to be put in by hand as an extra term, which broke this non-abelian gauge symmetry. You just have the symmetry, then you add one term in the Hamiltonian of the theory, which breaks the symmetry. But unfortunately, as a result, this model also breaks down at high energies. So there's a series of attempts all leading to models which break down at high energies. Okay, now comes Weinberg on his visit in 1962 at the age of 29 to Imperial College on the invitation of Abdus Salam, who was then a professor at Imperial College. Later, he would found ICTP in Trieste in Italy, and then he commuted between both places. I was Salam's postdoc in ICTP in 1981 to 83, but this is a much earlier period. And here, the topic was something called spontaneously broken symmetry. Now, this was an interesting concept, which I can't explain in too much detail, but I'll give you an analogy. This concept was useful in condensed matter physics, and it was useful in just ways of thinking about continuous symmetries. And Nambu was one of the people. He also got a Nobel Prize more recently, and also passed away recently in the last few years. One of the proponents of these ideas. You can read about them. But the basic idea is the following. Look at this bowl. Imagine this is a kind of metallic bowl with a bump in the middle, like this. And notice that the bowl has a rotational symmetry. Okay, but if I place a marble in the bowl, then obviously it's not going to stay at the center because the center is an unstable minimum. And so it will roll down to this circle which you see, and it will roll down arbitrarily to any point on that circle. We can't say which one. But once it has done that, then the symmetry is no longer there as far as the marble is concerned, because it finds itself at one place, and if I rotate the bowl, the marble will move to another place. Okay, so this is the idea of a spontaneously broken symmetry. Namely, the theory has a symmetry, but the ground state of the theory doesn't exhibit that symmetry. Now, in this example, notice that after the marble has rolled down, it can move without any cost in energy along this circle. I don't know if you can see my cursor, but it can move along this circle with no cost in energy. And that's a very interesting consequence of spontaneously broken symmetry. Namely, that the ground state doesn't have the symmetry, but there are many ground states related by the symmetry. It's quite mind-boggling, and it's something that you need to take some time to get used to. Okay. Now, the conjecture of Goldstone, which Goldstone, Salam, and Weinberg proved, was that whenever a continuous symmetry is spontaneously broken, then there are massless, spinless bosons in the theory called Goldstone bosons. Okay. Massless is by analogy with the fact that this marble requires no energy to go around this circle. Okay, of course, if it was that simple, then these three people wouldn't have to get together in 1962 and prove it. So it's much more complicated to prove, but I've just given you a picture of how this works. Okay, now the problem is that no massless, spinless bosons are seen in nature. The only massless particles we know of are photons and probably gravitons, the quanta of gravity, but everything else, all other particles, electrons, neutrinos, muons, you name it, quarks, whatever, they all have a mass, which is non-zero. Okay, and so no massless, spinless bosons are seen. So it suggests that at least for particle physics, this kind of realization of symmetry is not useful, because if it was true, then it would contradict experiments. Such particles would have been seen. However, these authors, even though they knew what was gauge symmetry, and even though Glashow had written his paper 2 years earlier, they didn't apply their theorem to gauge symmetry, and that was a loophole that they missed. In 1965, it was Peter Higgs in a single author paper, as well as Ongler and Brout in a separate paper, who considered the idea of spontaneously broken symmetry, but in theories with gauge symmetry. You see that I'm using the word symmetry repeatedly. It's the nature of this field, and it connects back with what I quoted from Weinberg on the very first slide. Now, what they realized was that if you naively apply Goldstone's theorem, then the spectrum of the model will indeed contain unwanted massless spinless bosons. That's Goldstone's theorem. But they realized that maybe Goldstone's theorem doesn't apply. Maybe we have to analyze the situation more carefully. And they, in fact, analyzed the situation more carefully and showed that when you have a gauge symmetry, then a change of variables takes the Goldstone boson away from the spectrum of the theory. And on the contrary, the spin 1 boson associated to gauge symmetry acquires a mass. It becomes a massive boson. And this looks very exciting, because broadly, this is the kind of theory that one is looking for weak interactions. Okay, a theory in which there is a spin 1 boson to be this W boson or Z boson communicating the weak interaction, but with a mass, but also with a symmetry. And so it seemed that gauge theories with spontaneously broken gauge symmetry are well suited to describe weak interactions. And this gauge symmetry, even though it's spontaneously broken, that's not considered by experts to be a correct language. The correct language is that it's hidden. It's realized in a very subtle way. And the resulting QFT still knows about this symmetry. And maybe the presence of that symmetry makes the theory consistent at high energy. So you see that now people were getting closer to finding the right theory of the weak interactions. And well, 2 years after that passed, if we were in the modern age with internet, everybody might have started working on the ideas of Higgs, Ongler, and Brout. But actually, Weinberg took 2 years, thought about it patiently, and wrote this paper. And this is the paper, a model of leptons. Steven Weinberg, you see at MIT, Laboratory of Nuclear Studies, written in November 1967, and it's only a 4-page paper. 3-page paper, sorry. In this 3-page paper, he published a formula that synthesized these preceding attempts, the work of Higgs and others, the work of Goldstone and Salam and Weinberg himself, the work of Glashow, the work of Schwinger, Marshak, Sudarshan, Feynman, Gell-Mann, Yang, Lee. Lots of people had built much knowledge about weak interactions, and he had basically read it all, thought about it all, and he synthesized it in 3 pages into a compelling theory. And although he modestly called it a model of leptons, it wasn't just a model. It was essentially what today we know as the theory of leptons. In fact, it's the weak and electromagnetic part of the standard model of particle physics. So let's take a look at this, some aspects of the paper, and then I'll pause for questions. So by all means, ask questions if you have them. Just give me one more slide and then you can ask. Okay, here's the opening paragraph of his paper. Leptons interact only with photons and with the intermediate bosons that presumably mediate weak interactions. What could be more natural than to unite these spin 1 bosons into a multiplet of gauge fields? This synthesizes all the ideas that I've tried to present to you in brief. And then he goes on to say, this note will describe a model in which the symmetry between electromagnetic and weak interactions is spontaneously broken, but Goldstone bosons are avoided by introducing the photon and the intermediate boson fields, these are the W and Z, as gauge fields. And he concludes saying the model may be renormalizable. He couldn't prove that. It was a very hard proof, actually. And renormalizable means consistent at high energy. If it wasn't, he wouldn't have made much of an improvement on Fermi's old theory. But in fact, he proved to be right, and eventually it was clear that the model is renormalizable. Now here's a little equation that I cut and pasted from his paper. And the beautiful thing about it is, including everything, notation and all that, it's very clear to any practitioner of particle physics what this equation means. For example, the first term is the coupling of electrons and neutrinos to the W boson. The second term is the coupling of electrons to a photon. A mu here is the photon, W is the W boson. Here there's a more complicated term, coupling particles to the Z boson. Okay, so, and these G and G prime are two coupling constants of the theory, which are loosely associated with the electromagnetic and weak interactions, though actually in a complicated way they mix. So that's the theory. So what does the theory do? It actually unifies the weak and electromagnetic interactions, though that was not necessarily part of the original goal. It incorporates parity violation. Okay, for those who know quantum field theory, parity violation can be seen by the presence of this matrix gamma 5. Gamma 5 is a very particular matrix in the Dirac theory which changes sign under parity. So if it ever appears explicitly, then under parity 1 plus gamma 5 will go to 1 minus gamma 5, and so the theory will be not invariant under parity. Okay. And it turns out that the way parity violation is incorporated, the Higgs ends up giving mass through its coupling to all the particles in nature. And you might have seen these popular expositions which say that it's the God particle because it gives mass to all other particles. I don't like that language much, but anyway, the important thing is that this was the first realistic theory which actually had a Higgs particle in it. It's precisely the particle that Higgs, Engler, and Brout predicted would come out of this kind of spontaneous symmetry breaking. Okay, so there are 4 new particles which were not seen in nature predicted by Weinberg's paper. The W plus minus, because W is charged, it has an antiparticle, so W plus and W minus are each other's antiparticle, and Z. All these 3 were discovered in 1983. Now we are in 1967. The Higgs boson discovered in 2012, okay, nearly half a century after Weinberg's paper. Okay, but this theory by Weinberg, which was independently found by Salam but not published in such a clear way, and which built on an older theory of Glashow, was not believed even till the mid and late 70s. I went to graduate school, that is, I did my PhD starting in 1976, and even in those years, people were saying, well, we don't know if this theory is right, it may not be right, and so on. But then it was proved that the theory is renormalizable, namely consistent at high energy. This proof won a Nobel Prize for 't Hooft and Weltman. That's a whole other talk. It's perhaps the single most mathematical work to have ever won a Nobel Prize, and they got the prize much later in 1999. But they did their work in the mid-70s, and once they had done their work, people realized that, look, this theory of Glashow, Salam, and Weinberg basically looked right. Now it looks even more right. It's consistent, and it fits what we know about the weak interactions, but it predicts some new particles. Maybe they are there. And in 1979, Glashow, Salam, and Weinberg got the Nobel Prize in Physics. Now, if you're looking carefully at this slide, you'll see that's before the W and Z bosons were discovered and much before the Higgs boson was discovered. Okay. The catch is that in the 1970s, around 76 or 77, there was an indirect detection of Z bosons. They were not actually found, but their effects or some effects were seen. Basically, I can show you, it's the effects of this term. You see this term with Z mu in it, the last term. Well, this big square bracket, some effects of that term were seen more or less unambiguously in an experiment. And that was enough to say the theory must be right, and the Nobel Prize is given in 79. Now, the Nobel Committee would have faced a lot of embarrassment if these particles had never turned up, the W and Z, but they were sure that they would, and they did. So that's how it worked. Okay, now I'm happy to pause for questions, and I actually would like some questions because I don't like giving a talk to an audience which I can't see or hear. So if you have a question, put it in the chat box or unmute yourself or do whatever you like, but please do ask. I hope I don't have an audience of 59 non-curious people. That would be really depressing. Everything was clear up to now? Chat box is empty. I don't know if it's accessible or not. I don't know if people are able to. Organizers, please, can you do something?
Hello, sir. Am I audible?
Yes, you're audible.
When we say spontaneous symmetry breaking, what do we exactly mean by spontaneous?
Yeah, thank you. That's a good question. So let me explain that. Before that, let me answer Shivang Yadav's question. Salam's contribution, actually, it's a little murky, because what Salam did was he was thinking about the same things, but he failed to publish a paper. Instead of that, he gave certain lectures on his theory, and he had a variety of different theories to propose, one of which was exactly the theory of Weinberg. Okay, but he had been working in the field and people knew about his work, and he had written up his lecture notes for a book, which was a conference proceedings, and it was those conference proceedings notes which were published 1 year after Weinberg's work in 1968, which rendered him eligible for the Nobel Prize. And this part of the work from 62 to 68, I think he did independently of Weinberg, but he did work with someone called Ward in Imperial College. And people sometimes say that Ward should have also shared the Nobel Prize, but then, as you know, it has a limit of three winners. Okay. So the question about spontaneous symmetry breaking, what is spontaneous symmetry breaking was the question, Kaustubh? So I stated it once, but I'll state it again, is the statement that a theory has a symmetry, a system has a symmetry, but the ground state or lowest energy state of the system doesn't have that symmetry. So in this case, the system is the bowl. The bowl has a rotational symmetry. Okay, but if I put a marble in the bowl and I balance it at the center, which is the symmetric point, still the system has a symmetry, but it's not the lowest energy state. The lowest energy state is when the marble has rolled down to this ring of minima, and there the system no longer shows the symmetry because there's a marble sitting at one point on this circle. So all points on the circle are not equivalent. One point is where the marble is sitting, and all the other points it's not. You see that?
So I was trying to understand the role of the word spontaneous here. So does it come from the fact that the equilibrium at the top of the hill is unstable?
Absolutely, that's exactly what it comes from.
Okay, thank you.
Thank you. That's a really good point. It comes from the fact that the equilibrium is unstable, and actually, in quantum field theory language, this looks very much like the potential energy experienced by the Higgs field, as it's called, and the Higgs field takes what is called a vacuum expectation value, which is the analog of moving from the unstable maximum to the stable minimum. So you're exactly right. Nice. Well, when I give a talk in IISER, I always expect great questions. So I already got one or two. Any more? Most welcome if you have any. Okay, if not, I'll go on. So let me briefly touch on a couple of works. One is Axions. So now, yes, please.
I'm sorry. There was another question in the chat from Amog.
I didn't see it. In some, let's see. In some, okay, small, slightly off-topic question: how were research papers communicated back in the day? Amog, it's off-topic, but it's a great question. They were communicated via preprints. So even when I joined graduate school, and actually for my first, 7-8 years of my career as a faculty member, we would type the paper on a typewriter. Then we would make hundreds of copies that we would put them in the post and mail them to people. One copy would be mailed to the journal as a submission, but we would also mail the papers to all our friends and to all the libraries we knew. Then people would drop into their library where there would be a shelf full of recent preprints, and because they were not yet published. That is what turned into the archive now. And then once it was published, then of course the library would subscribe to the journal, and then the paper would appear in the journal. But that could take 6 months. It was very slow pace at that time. Okay, let me go on. There are a lot of things more to discuss.
I think Harsh has a question. He raised his hand.
No problem. Raising
Yes,
hand
sir.
is no
Hello.
Yeah, go ahead.
Okay. Okay. Yes, I just want to ask, unless I missed it, I didn't see an equivalence symbol in the equation involving electrons and neutrinos. So, how does that exactly work?
Equivalence symbol. Okay, sure. That's because it's really not an equation. So I lied when I called it an equation.
All right.
It is really it's something else. It's called the Lagrangian. So you may know that any classical or quantum mechanical system has a Hamiltonian and a Lagrangian. These are two ways of expressing the dynamics of the theory. And this is a line from the Lagrangian. So the equation is L equals this.
All right, sir. Thank you.
If you want, for simplicity, just think of it as these are terms in the interaction Hamiltonian of the theory.
All right, sir. Thank you.
That's a perfectly valid way of thinking about it, which I should have said actually. All right, now axions. Now axions are hypothetical particles which sort of bring back this Goldstone boson idea. So sometimes ideas never die; they come back in some other form. And what happened was that in 1977, following some work by Peche and Quinn, Weinberg and also Frank Wilczek, another Nobel laureate, showed that a new kind of particle arises in a suitably generalized standard model, where the model has been generalized to explain parity and time reversal invariance of the strong interactions. Okay, so there's something called the strong CP problem, which is the problem, actually I should have said parity and charge conjugation invariance. Charge conjugation times parity. So there is a possible term in the strong interaction Lagrangian, which I haven't even discussed today, called the theta term. And that term, if it was there, would violate C and P, charge conjugation and parity. And there would be an arbitrary parameter, which is the strength of that violation. And if there's no principle to set it to 0, it could be non-zero and it would become quite a problem to account for experiment. It would conflict with experiment. But if we instead propose that there's an axion particle with a suitable coupling, then a shift of the definition of that axion field can absorb this CP violating phase and basically set it back to 0. Okay, but this is at the price of having a physical particle called an axion, which would, though it's a Goldstone boson, is not exactly massless because of some mechanism, some explicit breaking of the symmetry also. So it's called a pseudo Goldstone boson. And Weinberg in particular looked at the experimental signatures and found that this kind of axion would explain a puzzle, but its existence would not be in contradiction with known experiments. And people are actually doing astrophysical experiments to search for axions, even though to date there is no evidence that they do exist. Now, one funny thing that I like to talk about is that recently axions showed up in a different place. In topological insulators, which are by no means related to cosmology, they are pieces of matter which have certain properties which are topological. So they are insulators in the bulk and they are conducting on the boundary, and they are very, very interesting objects in condensed matter physics today, 2021. I mean, also in the last decade or so. And what people found was that the same mechanism which creates axions in these models creates them in topological insulator models, and they have been detected experimentally. So Weinberg and Wilczek's idea of axions, although it didn't work in cosmology so far, it might still, but it certainly works in Weyl semimetals. So that's a little thing to tell you that, you know, physics has this property that, you know, something which a nice idea tends to work somewhere. I don't know how to put it better than that. Okay, now let's go on to his work on cosmological constant. So Weinberg studied the cosmological constant, or the vacuum energy density. That's a natural part of Einstein's general theory of relativity. Now, observations at the time Weinberg was working, 1987, had put an upper bound of this amount on this vacuum energy density, and correspondingly an upper bound on the value of this cosmological term. But it was only an upper bound. At that time, it was thought that it might even be 0. But today, it's believed actually that the cosmological constant is non-zero, and that this is actually the vacuum energy density of the universe. Okay, I don't know, somebody is repeatedly calling me. Please excuse me for a second. Hello? What are these? Hello? I really don't know what's going on. Okay. Okay, so today it's believed to be quite close to that number. Let me say that if you have a positive cosmological constant, then it causes an effective repulsive force, and it's consistent with the fact that the universe is expanding and even its rate of expansion is accelerating. So that's the role of the cosmological constant, but it's extremely small, as you can see. Okay, in fact, it's much smaller than would be contributed by vacuum fluctuations of all the fields that exist in the standard model, and it's 10 to the minus 120 times what the naive calculation in standard model would predict. So as people say, this is the worst prediction in the history of science. 10 to the 120 is an unimaginable number. Okay, but what it tells us is that estimating actual vacuum fluctuations of the standard model is not the way to calculate the cosmological constant. Apparently, it's not given by just a crude estimate of vacuum fluctuations, it's something else. Okay, and what Weinberg did in a short paper was to argue that something called the anthropic principle puts a sharp upper bound on this number rho v. Okay, and this was the upper bound in those days. His theoretical calculation confirmed that this is sort of an upper bound, but it was based on a very controversial principle, which is still the subject of heated debate today. Okay, the anthropic principle broadly says that fundamental constants in nature take the values that they do because those values allow for the emergence of intelligent life which can study them. So the very fact that we are studying physics means that the fundamental constants in physics had to be of the values, range of values that they had. Otherwise, life as such could not exist. Okay, and let's try to understand how he applied this to the cosmological constant. The main point is that if it's too large, if there's too much vacuum energy density, then the repulsive force it creates will inhibit the formation of matter clumping together. Okay, so gravitational collapse of things will not happen, galaxies won't form, and then of course the universe as we know it won't form, it will just be particles floating around, not big solid lumps that we consider to be galaxies with stars, planets, black holes, and all kinds of massive objects, which are all basically bound gravitational objects, like the Earth in particular. Okay. So now in this principle is weird because it talks about something quite unobservable. Like if there's a universe where the fundamental constants are not these values, we wouldn't be there. So, how can we even make sense of that? So this is a very hotly debated topic. And there are some sensible arguments, by the way, on both sides. And it's worth actually engaging with them. Okay. So there might be a setup where the universe has different vacuum energies in different parts of it, and then maybe we could only exist in those parts where it takes these favorable values. But these are just words. Weinberg never liked abstract philosophy. He simply started with this and said, I'm going to do a calculation to find out what is the value of rho v, the vacuum energy density, such that if it's too large, stars and planets will not form. And he found with a little calculation, not too many lines, 3 or 4 lines, and again, it's a 4-page paper, that rho v is about at most 1 to 100 times rho 0, which is the mass density of the universe. Okay, so rho v is the vacuum energy density, rho 0 is the density in actual mass, including dark matter and visible matter. Okay, now recent measurements, as far as I could understand, suggest that rho v is a few times rho 0, which is non-zero and satisfies Weinberg's bound. But Weinberg also went on to write a very beautiful review of the subject of the cosmological constant, which played an important role to project it as a research topic. So that review has thousands of citations too. It's not just this one anthropic calculation he did, but the fact that he brought the cosmological constant into theoretical discussion at the time when cosmologists and astronomers were beginning to think that it's probably non-zero. So in a way, he propelled the theoretical field, or he played a role to make people think about it. Okay, now I'll move on. I have about 15 minutes. In this much time, I'll move on to the non-research aspects of his life, which are also very, very interesting. They do touch on his research, you will see again and again, but let me just say some words about him. Again, if there are questions, I'm happy to pause. I don't see anything in the question box, in the chat box. Just type them there, and from time to time, I'll take a look there. Okay. He was a masterful teacher. Now, all Nobel laureates are not masterful teachers, I can assure you. But Weinberg was, both at the technical and popular level. And he has a whole bunch of physics textbooks. And here's a list of them. Oops, sorry. Oops. Yeah, here's a list of them. The last one just this year. The last one maybe not so much a textbook as a collection of, it's a textbook of sorts, but it's like a review of what were the foundational discoveries of modern physics. So it's for a physics student, but it's less of an in-depth textbook and more of a survey. The others are all in-depth textbooks. Okay. Now, in particular, okay, so they are clear, lucid, logical, readable, but they don't always follow the standard approach. They are always phrased in Weinberg's personal way of thinking. Now, curiously, his gravitation book had a big, what I think today would be a lapse of judgment. Einstein's approach to gravitation was Riemannian geometry. He said space-time is a pseudo-Riemannian manifold, and light travels along geodesics, and principle of equivalence basically is about geodesic motion in this manifold. Okay, but Weinberg didn't like that, to take that too seriously. I mean, people used to say that geometry is the basis of gravity, and he wrote something in his introduction to this book. He said, too great an emphasis on geometry can only obscure the deep connections between gravitation and the rest of physics, because the rest of physics is not based on geometry. Okay, and this, I think, was a huge lapse, because he ignored the entire story of causality, light cones, and then closed trapped surfaces, black holes, which was just happening at the same time. The black hole information paradox, black hole entropy, black hole thermodynamics. These are revolutionary ideas pioneered by Hawking and Penrose. And basically, this book has no mention of them, except somewhere he says, sorry, I don't have time to review the great work of Hawking and Penrose, but he just doesn't do it. Okay, no modern textbook on gravity could do this, because these are central to research in gravity today, absolutely central. Moreover, of course, as you know, Penrose won a Nobel Prize, and black holes are real things. In this book, Weinberg was not at all sure at that time that they were real, but Hawking and Penrose, believing in their reality, pursued the topic in their own books. Hawking in particular has a nice textbook, very mathematical, very difficult, called Space, I forgot what it's called, The Large Scale Structure of Space-Time, Hawking and Ellis. But Weinberg somehow missed that whole thing. Still, for whatever it does, it's good. For its coverage of cosmology, it's good. But he missed a very key part of gravity in his textbook. Too bad. He wrote a number of popular books for the lay reader. And the first was called The First 3 Minutes, which is basically the first 3 minutes after the Big Bang, when the universe basically started to develop into the form that it would ultimately take. Discovery of subatomic particles, elementary particles, and the laws of physics. Dreams of a Final Theory, which I'm going to talk about now. And then something on science and culture, something about nuclear weapons, the world and the universe, to explain the world, and finally his last popular science book called Third Thoughts. All his popular books are really good. I recommend to any student to read any of them, but in particular my favorite is Dreams of a Final Theory. Let me come to it. First, let me say that The First 3 Minutes was a big bestseller. I'll show you here. It's even been translated into Tamil, maybe into other Indian languages, I'm not sure. It's a very lucid introduction to modern cosmology for the reader who is not at home in either mathematics or physics. These are his words. It was revised in 1993 because, you know, in that period, 80s, 90s, and even to some extent now, it's very dangerous to write about cosmology because experiments tell you different things every few years. It's a developing field, especially in this period, it developed a lot. But I think the currently available version is worth reading and reasonably up to date, though not completely so. Okay. So now for my favorite book, Dreams of a Final Theory. In this book, he goes to the heart of his beliefs about science and its future. And he tackles many very thorny and controversial concepts. He tackles them with clarity and bluntly, but with no aggression. And his views are not widely accepted. Even there are one or two things I would also question, but he tackles them. Reductionism, how theory and experiments interact, how beauty influences our choice of theories, the relevance of philosophy of science to him, to Weinberg, I mean, his perspective on that. And at the end of the book, he expresses his views on God. So he has a whole chapter on God and religion, which I think would not please a lot of people. And also a chapter on the superconducting super collider project, about which I'll speak shortly. Okay, so it's quite a book. Let me talk about reductionism. This is a very important slide. I think students will get a lot out of this. He uses a sequence of why questions. You remember in the opening of this talk, I showed you an interview with Weinberg where he says, we want to know why things are the way they are. So he starts with this question: why is chalk white? Answer: because it doesn't absorb much visible light. So it reflects visible light in all the range of frequencies and it looks white. Why doesn't it absorb much visible light? See, the next question is about the answer to the previous question. Well, because its molecules do not have the right quantum states to jump to after absorbing photons. Okay, photons of visible light. So visible light is unable to excite chalk molecules, calcium carbonate. Okay, so there's an explanation which is behind chalk, namely by an arrow it leads to chalk, the property of chalk. Okay, so why don't molecules have those states? Well, because the quantum mechanics of particles and particle-light interaction tells us, first of all, that molecules will have those states that solve the Schrodinger equation, and Schrodinger equation gives us the molecular states, whether by analytic calculation for very simple atoms or by numerical computer simulations or whatever way you do it. But basically, this quantum theory of particles and light is what tells you that the molecules of chalk don't absorb visible photons, which tells you why chalk is white. Okay, but why do particles interact with light the way they do? Because of the Standard Model, which actually includes quantum electrodynamics. In this particular case, only the quantum electrodynamics part of Standard Model is being used. And electromagnetism has this standard vertex, which you can see down here, with an X, and a gamma. The gamma is the photon. And basically, this is the 3-point vertex of quantum electrodynamics, which says that every charged particle can absorb or emit virtual photons and continue on its way. And there's a particular statistical weight to be assigned to this figure and a set of rules. From the figure, by putting it together, we can get these amplitudes and probabilities for various processes. Okay, and that tells us the way particles interact with light. There's no way we can deviate from that, because that's what this theory says. Okay, so then Weinberg concludes that the structure of the Standard Model is largely fixed by quantum mechanics, relativity, and the menu of particles it contains. There's not much option to add terms in the Hamiltonian or Lagrangian as we feel like and tweak it to fit an experiment. It's not like, well, the experiment doesn't agree with theory, so let me add a term with a small number 0.01 in front and maybe vary that number, and maybe somewhere it will start agreeing with the experiment. There are not terms available in Standard Model that you could add. Okay, because they have to satisfy this consistency which comes from quantum mechanics, relativity, and renormalizability. Very, very important. Okay, so this is the way Weinberg motivates reductionism, that ultimately from chalk you can find your way back to quantum electrodynamics. Now he emphasizes this does not mean that the person who wants to study chalk will find quantum electrodynamics useful or should stop using any other chemical method. A person who wants to do chemistry cannot say, I'll stop using chemical tools and I'll use quantum electrodynamics. It's not useful. It's just conceptually useful that these arrows exist. And he emphasizes that sometimes we can't actually trace the arrows precisely, especially in case of biological systems. But he says we have enough evidence to believe that there are arrows, and that's what brings us to the concept of final theory. So he says the standard model in these kind of examples is like a approximate final theory to which all physical phenomena, be they in chemistry or in biology or in condensed matter physics, can in principle be traced back. Okay, but standard model, even though he was one of its developers, is not complete because it doesn't describe quantum gravity and it has other visible incompletenesses. So Weinberg says, well, there should be a final theory that's even behind the standard model, one more arrow, and his dream is that such a theory may exist and may be found in the future, and that's basically why he writes this book. Now he comments about the sociology. He says, talk of a final theory seems to enrage some philosophers and scientists, make them really angry. He says this is partly a reaction to the various silly things that might be meant by a final theory. For instance, that discovery of a final theory in physics would mark the end of science. He emphasizes that nowhere he is saying such a thing. He does not think that discovery of a final theory would mark the end of science in any way. Let's see his quotes on that. He says, of course, a final theory would not end scientific research, not even pure scientific research, nor even pure research in physics. Wonderful phenomena from turbulence to thought. I can also help Weinberg by adding superconductivity and so many other things, quantum Hall phenomena, so many things, Bose-Einstein condensation, whatever it is, many of the phenomena that we see will need explanation even if a final theory is discovered. A final theory will be final in only one sense. It will bring to an end a certain sort of science, the search for those principles that cannot be explained in terms of deeper principles, namely the end of that sequence of back arrows which I drew for you on the previous slide. Now, of course, Weinberg goes on in a later chapter to talk about string theory. He says string theory has provided our first plausible candidate for a final theory. String theory is very demanding. Few of the theorists who work on other problems have the background to understand technical articles on string theory. Some of my colleagues have reacted to this unhappy predicament with some hostility to string theory. I do not share this feeling. He says string theory provides our only present source of candidates for a final theory. How could anyone expect that many of the brightest young theorists would not work on it? So this is Weinberg putting his views right out there. At the same time, he says neither he's claiming that string theory is right, nor standard model is right, nor either of them is fundamental. And he said that maybe the final theory may not have any element of quantum fields in it or strings in it. It may be something else altogether. He doesn't know. He simply says we should or we can look for a final theory. It may exist. It may be possible to find. That's really his point. So that's this book. Now it's 6:10. I think I'm almost completing an hour. If I can have 5 minutes, mostly I'll talk about, I'll show you some clips from Weinberg and we'll end. Is that okay? Okay, since no one's saying anything, I'll assume it's okay. Okay, here Weinberg has been open and fearless about his opinions on social issues. Some of the most important ones for him were religion and science, science funding, and gun laws. And gun laws he encountered because he moved to Texas. Otherwise, probably he wouldn't have encountered them so harshly. He gave an interview to Times of India in 2015, which may not make everyone in India happy. He said, it's nonsense to say modern science existed in ancient Greece or India. Now, he's very concrete, but note that this is a person who has actually read a lot of the material based on which he's making the judgment, both ancient Greece and ancient Indian writings. And it's not that he doesn't respect them, but he has the following precise criticism. He says, our predecessors in the ancient and medieval world often believed that scientific knowledge could be obtained by pure reason. Where they understood the importance of observation, it was passive, not the active manipulation of nature that is characteristic of modern experiment. This line is really very deep. Active manipulation of nature that is characteristic of modern experiment. You don't sit and watch things, you make things happen and you note down what they do. Okay? And he says further, their theories of the physical world were often muddled with human values or religious belief, which have been expunged from modern physical science. They have no role in modern physical science. Human beings and religion and values have nothing to do with how fundamental particles interact with each other. So this is Weinberg being very blunt about ancient science. Again, not saying that in fact, he has said very clearly in the rest of this interview and elsewhere that they were very good, very much relevant progress, including postulating the atomic theory, which happened in ancient Greece, but also in ancient India. These were very good, but he says it was not modern science that existed. It was modern for its time. It deserves its respect, but it's not what people understand today as modern science. Okay, now please listen to him talking about religion. A very brief clip.
I do spend probably a little bit more time than I should on religion, and I have a certain amount of hostility to it. I think the most rational reason for it is because of the harm that I see it does. We were talking about that earlier. Many people do simply awful things out of sincere religious belief, not using religion as a cover, the way Saddam Hussein may have done, but really because they believe that this is what God wants them to do, going all the way back to Abraham being willing to sacrifice Isaac because God told him to do that. Putting God ahead of humanity is a terrible thing. Yeah.
Okay, like it or don't like it, that's Weinberg on the subject of religion. Let's move on to Weinberg on the Super Collider. The Super Collider was a project proposed in the United States to be a particle collider reaching energies up to 20 TeV, tera electron volts. In the 1990s, there was vigorous debate on whether the US government should fund it. And interestingly, they started to fund it and funded it until a significant part of it was actually built. They spent, I think, $1 billion on it. Okay, and Weinberg strongly fought for it to be fully funded. And for this, he had to oppose both politicians and other physicists, including fellow Nobel laureate Philip Anderson, a condensed matter physicist, who opposed this collider. I should tell you that Freeman Dyson also opposed it. In fact, in 1995, I had dinner with Freeman Dyson in Princeton, and he was telling us how he successfully opposed the Super Collider and why. This point of view of Anderson is very important. It's very worth reading. Anderson has a book called More is Different, or an article. He has an article and a book. And somebody, not me probably, should give a talk like my talk on Weinberg. Somebody should give a talk which describes Anderson's view of physics, because it's a different view and it's also very relevant. And I just want to say this to students, don't try to now pick Weinberg's view or Anderson's view. First, try to do work as good as Weinberg or Anderson. It doesn't matter. We get all on top of ourselves and start fighting the view of famous people. Not a good idea. Just listen to the views and struggle to become as good as any of these people. It doesn't matter who. Okay, so Weinberg spoke to US Congress, their parliament, and he was asked as an expert, and he spoke in favor of the SSC, but he didn't succeed. The project was cancelled in 1993, and Weinberg was really shattered. He became pessimistic about future accelerators. Here's a brief clip about him talking about that.
And my pessimism comes partly from my experience with another large accelerator project, which was canceled by a vote in the House of Representatives in 1993. This was an accelerator called the Superconducting Super Collider, and I'm going to abbreviate that to SSC. The SSC would have been even bigger than the Large Hadron Collider, a 53-mile circumference, and it would have accelerated particles to 3 times the energy that can be reached at the LHC. And it would already have answered these questions that we're hoping to see answered by the LHC. We struggled to get it funded. About $1 billion was spent on it, and then it was killed, as I said, by a vote in the House of Representatives. One thing I learned during the fight to get the SSC built was that no scientific discovery is remotely as important to a legislator as the economic interests of his or her own constituents. And this is not something evil. This is the way democracy is supposed to work. Legislators are supposed to represent the interests of their constituents. The problem is that it all too often turns out to be the short-term interests, and they don't provide enough wisdom and guidance so that their constituents will respond to the long-term needs, not only of their own little district, but of society in general.
Okay, now we are nearing the end. Now let me tell you the story about guns. I think it might amuse you. So Weinberg was in Texas, and in Texas, all over the US, of course, you can get a license and you can have a gun. But there are different laws in different states, quite different. And the laws can restrict where you can carry a gun to. And they also restrict whether when you carry, you have to show the gun. That is, it has to be worn outside your body, maybe on a belt, or you're allowed to hide the gun. If you show the gun, at least the people you are with will know that you have a gun. If you're hiding the gun, that is called concealed carry, then it's a situation where you may have a gun and other people don't know that you're carrying a gun. So the laws say different things about these in different places. Until 2016, you could not carry a gun to a classroom in the University of Texas or in any university. They changed the law in 2016 saying, yes, students can carry guns to classrooms, but by the way, they still could not carry guns to research labs. Laboratory is considered a place where a gun can be dangerous because it could cause an explosion or a fire, okay? But a classroom is not like that. Of course, it can kill people, but somehow the culture is such that the right to carry guns is very, very prominently felt by many Americans. And so this happened. But understandably, Weinberg was not very happy. They even made it against the law for anyone, even a professor, to ask students if any of them are carrying guns. So the student could come into class with a gun inside their jacket, and the professor can't even say, does anybody here have a gun? And Weinberg found that very creepy, as would I, frankly. Okay, so he got mentioned in all the newspapers. Interesting thing is, he opposed the law, obviously, and said, I will put it into my syllabus that the class is not open to students carrying guns. But some students opposed this. Right-wing commentators actually wrote to the press and said he should be fired from his job. And the university did not support him in the sense they said, look, Weinberg, you may be anybody, but the law is the law. You can't break the law. This is Texas law. So in the end, he basically lost his battle, but luckily he was teaching some advanced astrophysics course with 20-25 students, and probably there was an implicit agreement that these 20-25 students would not bring guns to class. The real worry would have been of a much larger body of students, probably not the ones who would attend a PhD level course bringing guns to class. But it gives us a little insight both into Weinberg and into the United States. I'll close now with a few quotes from Weinberg. Here are two quotes which tell us his view about the importance of theory. Time and again, physicists have been guided by their sense of beauty, not only in developing new theories, but even in judging the validity of theories once they are developed. So he goes on to say, there's nothing in any disagreement between theory and experiment that stands up and waves a flag and says, I am an important anomaly. It takes theory to explain which are the important experimental observations. So he's trying to say, people think that, experiment influences theory, theory influences experiment. Theory has to be made, then experiment tests it, then new theory is made. But he's saying that experiment by itself doesn't test a theory, because actually any theory will have a lot of experiments that disagree with it for different reasons. Most often because either the calculations from theory or the experiments themselves are just wrong. They were not taking into account some effect that when they realized to take it into account, the agreement held up. So there are anomalies at all times. And he says, we don't know which are the important ones which flag that the theory is in trouble. Okay, and he says theory actually is a good guide to tell us about that. Now, on the other side, he had some experimentally oriented comments which are equally important. He says, we don't know what the Large Hadron Collider is going to find. If we did know, we wouldn't have to build it. Here he's saying that, you can do any amount of theory, but experiment gives you a final decision on whether something exists or not. And he also said scientific theories cannot be deduced by purely mathematical reasoning. So note these two types of comments. 1 and 2 seem to be on one side, 3 and 4 on the other, but all of these are from Weinberg. Couple more quotes. This one is perhaps very relevant nowadays. He says, if J.J. Thomson had been directed to work on practical problems, he would have developed a better steam boiler instead of discovering the electron. And this is an attack on people who say that we should work on applicable problems applicable to society, because the impact of the electron on society was way more than any number of steam boilers might have had. He also said the International Space Station was sold, that means advertised to the public for funding, as a scientific research laboratory. It has produced nothing of scientific value. His claim is everything that it does could be done from the Earth with probes up in the sky, but not with human beings sitting up there. The purpose of sending human beings up there is, there's no purpose according to him in that, because all they have to do is put some switches on and off, which they could equally well do from Earth. And finally, on climate change, he says it is foolish to bet against the judgments of science. And in case of climate change, where the planet is at stake, it is insane. So, okay. And I'll leave Weinberg to have the last word, a very short quote, and then we'll end.
What we need is for those of us who care about government support for all the things our society needs to unite, to help shift the balance of our economy more away from private goods in the direction of public goods, where the real needs of our society are. The real needs of our society are not for more consumer electronics, but for education, healthcare, scientific research, and so on. And this means higher taxes, which is a hard sell in a time when an anti-tax mania has afflicted the American public. But it's only in this way that we can get adequate funding for all the things that our society really needs, for education, for healthcare, for infrastructure, and all the others, and also for science of all sizes. Thank you.
Thank you. Anyone there? Okay, I see people. Let me answer the questions in the chat box first. What are vacuum oscillations? So, when you have a field like the electromagnetic field, then it is subject to quantum fluctuations. I don't think I used the term vacuum oscillations, but vacuum fluctuations, which is a different thing. It's very much like the 0-point energy of a harmonic oscillator. These fields have 0-point energy, and the combination of all 0-point energies from all the modes contained in the field is the vacuum fluctuations of that field. Okay, does Weinberg think that there could be more than one final theories? I think his point, obviously nobody knows, but I think his point was that there's one final theory and that we can find it. Other people say there may be one final theory, but we'll never find it. That's another approach. Okay. Yeah, Kwanit is asking about the late 19th and early 20th century, and then when people said physics will be over, can we ever pinpoint a final and exact theory? Yeah, all this, Kwanit, I would strongly recommend you to read the book. He addresses this. He goes into the detail of what people said at the end of the 19th century, and he explains why he thinks it's not the same as what he's saying. He says that in the end of 19th century, people said physics is over, but they didn't think that physics can explain chemistry or biology. So they had complacency that physics is a closed subject, chemistry has different rules, biology has different rules, physics is not supposed to go there. Okay, so he says physics looked to be over only within the domain of what was thought to be as physics. But now what he is saying is that the final theory, which is a physics theory in his mind, would be the final beginning from which all phenomena, all material phenomena come. Okay, quite a different prospect. But nobody claims, not even him, that 200 years later the final theory will be disproved. But please remember, no theory that has ever worked in history of science has ever been disproved. It's just found not to be accurate enough. Newton's laws are not disproved. Newton's laws are used every time you run a car or build a bridge. Okay, they only break down at short distances. Classical mechanics is not disproved, but it breaks down near the velocity of light. So any final theory may break down at some frontier of energy or size. That's always possible. The theories which are correct don't get disproved. Okay, they get incorporated into a bigger theory as an approximation. That can happen if the standard model is such an example. Probably it would get incorporated into a next final theory. And okay, Weinberg speculates that there is one, but you may be right, there may be many. It may not be exact. Yeah, it could be refined more and more. But again, he emphasizes that you cannot refine these theories in a simple way. They don't have those kind of parameters which can just refine them. They can break down. Remember, we could not refine classical mechanics in any way to explain the hydrogen atom. We had to change the theory and say it's not valid in that region of distance. So this can happen. Of course, it can happen. And the book is not called Prediction of a Final Theory. It's called Dreams of a Final Theory. He's given quite logical, coherent reasoning why there should be, in his opinion, such a theory. Yeah. Again, Konit, if it breaks down, how can it be final? Classical mechanics, when found by Galileo and Newton, was the final theory explaining the motion of the planets and also of falling bodies on the Earth. And it's perfectly valid final theory for that even now. Okay, but there are more degrees of finality because it breaks down at short distances. Please try to understand that breaking down doesn't mean we take the theory and throw it in the garbage. Okay, just be very clear. Tomorrow, somebody will build a bridge, maybe in Pune. Okay, they are not going to open Schrodinger's equation or let alone quantum electrodynamics or still less string theory to build that bridge. They are going to use Newton's laws to build the bridge. Okay, Newton's, Hooke's, anybody's law which tells you about elasticity, about structure, about mechanics, about dynamics, about motion, about vibrations. Classical physics. It's broken down, but it's not thrown away. Don't ever think that what we are doing today is tomorrow's garbage. No, never happened to anybody. Never happened to Newton. Newton is venerated today. Galileo is venerated today with good reason. The theories broke down, but they are not thrown away. They broke down because their domain of applicability going into regions which they could not have accessed. Newton had no access to distances of the order of a Fermi or even an angstrom maybe, and much below that. And that's where it breaks down. That's the point. It breaks down somewhere. It doesn't just break down. Okay, please don't think of it as a house exploding. It's not like that. Yeah, there's a difference between a final and a universal theory. No, I think Weinberg's final theory is a universal theory that he proposes. And please note one thing. Every experiment that has ever been done with elementary particles till today, 25th September 2021, is explained by the standard model of particle physics with a few anomalies. And many anomalies have come, but they've also gone away with better calculation or better experiment. You might know that there's currently going on muon G-2 anomaly, but it may be real, it may not be real. Okay, if it's real, then we have to see whether the standard model can be tweaked. If not, it might actually break down in some region, but it has to do so without violating all its successes. It's already successful to many decimal places. You can't just, so there's not a difference between final and universal theory. His word final is that it's at the back of a chain of arrows and there's no arrow behind it. You can always say, how do we know there's no arrow behind things? But don't forget one more point. This is also, I'm a bit passionate about this. People found substructure in all particles like neutrons, protons, pi mesons. They found that there are more fundamental things inside. Nobody has found substructure of an electron ever. There's absolutely zero evidence today, more than a century after its discovery, that the electron is made of something else. Okay, so it's easy to say that how do we know this won't continue? You can say it, these are words. Okay, but our experience doesn't suggest that everything will continue the way it already happened. Matter was broken into molecules, into atoms, into nuclei and electrons, but nobody has broken electrons. Nobody has any reason to think that they are breakable into constituents. So life is like that, So, I mean, just to say that you can't dismiss Weinberg's argument, but it's not a proof. Yeah. Somebody had a question.
Yes,
Yeah.
can you hear me?
Please, yes.
Yeah, first of all, thanks for such a nice talk.
Thank
You said that even before the discovery, Weinberg and other two people were given the Nobel Prize, and that is because WNZ was hinted in few of the some results, right? Can you please talk a
Yes,
bit about
okay.
that? As well?
Okay. So what you can Google is the phrase weak neutral current. Okay. Now let me explain what's a weak neutral current. Supposing I scatter an electron against another electron, then we know very well that this scattering is well described by the exchange of a virtual photon between them. That's electrodynamics. Now, it turns out that if you hypothetically do this experiment more accurately, there's an extra term which cannot be explained by electrodynamics, which comes from exchange of a Z boson between the electrons. Okay. Now that's called a weak neutral current because it's coming from weak interaction between electrons, and it's a neutral current in the sense that the Z boson has no charge. So it connects an electron to an electron, not an electron to a positron or to something else. Okay. So these weak neutral currents were unambiguously predicted by Glashow-Salam-Weinberg theory, and they were found in 1976 or 77. Okay, and there was no other theory around which predicted them, and because of that, and not just that they were found, but of course their magnitude was what you get by calculating from Weinberg's theory. Prediction is not just that something will be found, it's that something will be found with this number associated to it. The number is very important. So people judged by 1979 that, well, the evidence is so solid that if this theory was wrong, we wouldn't be able to explain weak neutral currents at all. And the theory seems to explain them very well. And this is, by the way, how any theory is judged to be correct. By evidence. Well, one thing, again, people sometimes feel is that seeing a particle is more direct. We call it direct detection. And this experiment we call indirect. But I can assure you that nobody in Geneva is sitting with binoculars and saying, oh, there goes a W particle, there goes a Z particle. That's not how it was seen, right? It was seen because it hit some apparatus, it was absorbed, it gave some effect. So it's always indirect. All modern experiments are indirect observations. There are no direct observations. But obviously, seeing the particle created sounds better. I mean, there's no doubt that it is better, but it happened 4 years after they got the Nobel Prize.
Thank you. Yeah.
Thanks for the great question, people. I should be going, but if you have one more short question, maybe. I think a lot of people have left anyway. So, yeah. Shall we close now, organizers? Somebody has raised a hand. Mayur?
So I think Mayur.
Hi. So you said that Weinberg, while describing gravity, so he didn't much like the term geometry. So can you shed more light onto that? So what he describes in his book Gravitational Cosmology?
Yeah, what basically he does is to, the Einstein equations are described by Riemann curvature. the Ricci scalar, which is derived from Riemann tensor, is the scalar curvature of space-time, of the metric of space-time.
Yeah.
Now, Weinberg cannot run away from that. That's the reality. That's how Einstein wrote it, and that's been checked by experiments, and it's true.
Yeah.
So he explains it that way. But there are ways of doing the calculations which are just algebraic. And there are other ways of doing calculations where you start to think about what is the causal structure of space-time. Namely, it's non-trivial in a curved space to ask what is in the future, what is in the past, and what is space-like separated to me, which I cannot even access because the signal would have to travel faster than light. That is called causal structure.
Okay. Yeah.
Okay? Now, Weinberg just doesn't go into that. But if you see, black hole is the quintessential object that the moment you cross its horizon, the space-time structure changes.
Yeah.
What was space and what was time become interchanged. The light cone tips over.
Yeah.
He wasn't impressed with all that. Okay? And he implies without saying so bluntly that black hole is a very exotic solution of Einstein equation. All you can say is, well, it describes the metric of space-time outside any solid object in vacuum, that is outside the object, like radial electric field, but there's nothing like horizon and all. He doesn't say it, but he implies it. So he missed the reality. Black hole is the most common object in the universe.
Yeah. Okay.
So, he would have realized that later in life. And I don't think he was that proud of that book. So he rewrote it as a book on cosmology, which had less gravitation and more cosmology.
Okay. Okay. Thank you.
Yeah. Okay. We stop now. Sorry, it went a bit over time. Thank you all. Thanks for your great questions. And really thank you all. Bye then.